Okay, the whole concept, well, we have to, because every time we define a function in any one of our examples, we always say that the function f is continuous and differentiable. Those are a lot of times interchangeable because if it's differentiable, it has to be continuous. So really, I don't have to say it's continuous because if I say differentiable, it's automatically continuous. But now we have to get to the topic when we talk about what is continuity. How do you define something continuous? Okay, now let's put it in math terms. Put it in math terms. Okay, it's
defined over all the variables.
Yes, but now how do you prove that? But everything you guys said is absolutely correct. Is absolutely correct. That would take you too long because you have to do it to every point along the graph, along the function. So that's what we say. And this is why up until now, when we talk about limits, how do we take them? If I gave you a function, if I said the limit as x approaches 3 of 4x squared plus 2x, what would you do? Yeah, just upload and input the 3. So let's see what happens at 3. Right. So we know that for this function, f of x, as x approaches 3, the limit value is 42. Because that's where it's approaching. Oh, yes, I'm sorry. Yes, it's amazing how big difference that makes. So, and this is a continuous function. Because if we graphed it, we know it's going to be, we could take out a 2x. So the intercepts are going to be at 0 and 1/2. It's a positive function, so it opens up like this. It's a continuous function. It goes everywhere. It doesn't have a point. It's a smooth curve, so it has derivatives everywhere. And we can find the limit at any point. But what we have to, what if we have a semicircle? Okay, first off, is this a function?
No, or yes.
How do we tell? Horizontal line test, it's a vertical line test. The horizontal, I'm not sure. Then, yes, it is a function because it passes the vertical line test. Is it 1-to-1? No, because it fails the horizontal line test. So being 1-to-1 is not a condition for continuity or functions. How about if we had a function that looked like this? Semicircle. Is that a function? Yes. It's not 1-to-1. Can we take the limit at 2? Of our function? We can also take, but there is a problem. Unlike this example up here, let's say this is 3. Whatever that is, whatever that number equals, f of 3. All our examples, we always said in our domain, here's A, here's B. As it gets closer to C, as x gets closer to C, and this is our C value, our f of x approaches L, the limit value. This is that point there. We always do it this way, and we do it from this way. Those are called two-sided limits. They have to both approach from both directions, and they have to approach the same number. So as our x's get closer to 3 from both sides, our y values get closer to L, the limit. We can't do that with this. How do you test the end bounds of a finite function? So I can't approach this value from, this is my C value. I can't approach it from here. Because first off, there's no graph. I can approach it from here. And if you see, the closer I get to C, what's our limit value approaching? 0. But if I put it over here, as I'm approaching C from this side, it's going to infinity. There's a problem, which is why we now introduce what's called a one-sided limit. The limit of f of x as x approaches C from the left is L. This is as x approaches C from the left. How do I know it's from the left? It's from the negative side. And then the other argument is I'm approaching C from the right. Because now we can look at closed domains. In the past, there were always open domains, usually going from infinity to negative infinity, or from A to B. And now we're going to do the same thing now with closed intervals. Where? Now, if it's like this, if you only have a one-sided limit, these endpoints are called boundary points. Endpoints of a closed domain. So let's look at limits at boundary points. And review real quick. How do we find our values of C? What C's do we use? Because we can use any C we want to. And if we use the C here or here, if we put 0 as our C, is that going to give us anything special? No. Because as our X values approach 0, what's our Y value approaching? 2. And I can do it from both sides. So typically, the C values we choose are where something happens, where it's asymptotic, where it's undefined, where something's going to happen. Because anything else is no problem. Let's look at what happens there. In our case, it'll be the boundary points, yeah. So now we're gonna look at limits at boundary points. The easiest way I can show this to you is with an example. The domain of the function f of x equals 4 minus x squared radical is negative 2, 2. Its graph is semicircle. Find the limits as x approaches negative 2 and as x approaches 2. How do we do this? Here's our solution. Let's look at as x approaches negative 2. How can we approach the value negative 2 in our function? Right, so we have to take the limit as x approaches negative 2 from the right of our function. 4 minus x squared and then for the other half, as x approaches positive 2, we can only approach that from the left. Very good. But the first thing you always want to do is just plug it in there. If it works, it works. If it doesn't, it doesn't. Then we try something else. What's that? And that's what we're looking for. Yes. So we first plug it in there. So we have 4 minus negative 2 squared. 4 minus positive 2 squared. 4 minus 4. 4 minus 4. And we got 0. And that's the important thing, because now, since they're both approaching a set value, do they have to approach the same value? No. It just so happens that they both two approach a semicircle. What if we had only a part like this? What if our domain now was from 0 to 2? Would they approach the same value? No, they don't have to, because as we're approaching a value from the right, it's approaching the limit value. As we're approaching this one from the left, it's approaching its limit value of 0. So let's say that's 2. They don't have to approach the same value. They just have to approach a value, and it has to be in the range. The domain of your variables have to reach the domain. Be a value in the range. So the domain here, the range there. So it doesn't have to be the same. It just so happens in this one it does, because it's a semicircle. Let's look at this one. For the function graphed below, find the limits at x equals 0, 1, 2, 3, and 4. Think about what we talked about today, too.
One at a one.
Ah, y'all agree? Y'all agree? Okay, let's see this. Let's make our chart. So this is going to be one-sided from the right. This is going to be one-sided from the left. And this is going to be two-sided. And here are our x values. So the first one, we have at 0. Can we approach it from two sides? Can we approach it from the left side? Can we can't approach the left because it goes infinitely. So this one does not exist. What is approach from the right? It approaches 1. Let's look at this one again. Since this side doesn't exist, it's not defined, I look at this side. So this one's also 1. Two-sided means I look at both sides. Is it approaching a value? This one on the left side, I can't do it because there's no function. But the right side, I can use it. Let's look at the next one. At 1. Let's look at two-sided. At 1. What's happening at 1? When you're coming from the left, what happens? Where is it approaching? When you're coming from the right, it's approaching. Because they don't equal the same value. Yes. Two sides, if you're doing two-side limits, they have to approach the same value. But if you're doing one side, it has to approach something. So the one-sided limit left. If I'm approaching 1 to the left, what do all these numbers seem like it's approaching? And if I approach it from the right, it's approaching 1. Right. On the one-side limits. And okay, notice, since they have different values, two-sided cannot exist. Does not exist because it doesn't exist. There's nothing there. It's not 0. It's not a different value. It just doesn't exist. So that's why these two are the same. So let's look at number 2. Do number 2. You see what you get from there. So at 2. From two-sided, what do we get? Do we approach the same value?
Yes.
What value is that?
1.
Yeah, because from the left. From the left side, what do you get? On the right side? So since both of these are coming to the same side, you get the same answer.
So if the two side going to be defined the same on the one side.
It should, if it has a limit, it'll be on both sides coming together, or if one side doesn't exist, if it's not even there, then it has to match the other. But if they're two different values, it doesn't exist. Because this is where also we're getting close to defining the concept of continuity. In order to be continuous, the limit has to exist and it has to approach from both sides, and it has to be the same value.
That's,
Yeah, so I'm jumping ahead, of course, but I'm giving you guys heads up on this. We're doing number 3. Need the picture. So what do you do number 3? What is it approaching? On two-sided, it's approaching 2. On one-sided left, what's happening? And the right-hand side is approaching 2. And at 4, the last one we're looking at. What's happening here?
it's one-sided, right?
So coming from the left side, what's it approaching? Very good. Very good. Yeah, as long as it's not defined, there's nothing there, then these are. So next, let's look at piecewise defined functions. Because obviously our graph we just looked at was a piecewise defined function. How do we put this? Because a piecewise defined function has multiple parts. Equals A, B, C, when X is less than 0, when X is equal, let's see, C, when equals C, and when X is greater than C. For the first one, f of x equals a when x is less than c. What kind of limit can we find there? Is it one-sided or two-sided? And it's one-sided from the where? Yeah, because since that's less than, it's coming from the left. And that has to, our limit value has to equal that a value. When x equals b, is when x equals c, we got our function equal to the b value. How do we find that one?
That's two-sided.
That's a two-sided. Right. So we just put there f of x equals c. Or as x approaches c. So that equals the limit, and that equals our value b. when x is greater than c. Our limit as x approaches c from the right. Very good. Actually, I shouldn't call those limits L. This is L, this is M, and this one's N. Because they don't have to be the same limits. As we saw, it doesn't have to be the same numbers. Let's further, because remember, the epsilon delta proof proved limits. For one-sided limits, using epsilon and delta, we see that for one-sided right limits, we have the limit as x approaches c from the right, f of x equals L. For every value that's to the left or to the right of c. For every x to the right of c. Then there exists an epsilon such that our f of x minus L is less than epsilon whenever when and delta is greater than 0. Think of what this means. F of x minus the limit is less than some epsilon. Whenever x is greater than c, but less than c plus delta. Remember, what are we doing here with our delta? What value is delta approaching? It's going to approach c. Because yeah, normally it approaches 0, but we want, if this is c and this is c, that means x then is approaching c, which is the h is goes to 0. So that's right. So from the right hand side, we start from the c value, which we're looking for a limit, all the values to the right of it, and it gets infinitely close. Because the smaller delta goes to 0, the closer that x goes to c, and then we go to our limit. Because remember, f at c has to equal L. What do you think the left side's going to look like? Exactly. Only thing we're going to change is on the left-hand side, we'll have c minus delta is less than x is less than c. The rest of it will be the same. So I'll write that in there. One-sided left limits. We have f of x minus L is less than epsilon, where C plus or C minus delta is less than X is less than C for all D delta greater than 0. And that's what that one finds for us. So again, the larger, the smaller delta becomes, the closer C and X become the same value. And once we have X and C is the same value, then the f of C equals our limit L, which is by definition what our whole function is about. That is, again, what we're trying to prove here. So let's look at our third example. Try to prove this one. Try to prove this one. Remember, epsilon is greater than 0. That's always given. That's always true. Then what do we have? We have C is our 0 point. This is our f of x. F of x is equal to the radical x. This is our limit point. L equals 0. So this is epsilon is given greater 0. We need to find a delta greater than 0 that shows or proves, proves that our f of x minus L is less than epsilon when C plus delta. Why do we use C plus delta on this one? It's because it's from the right, exactly. So let's plug in what we know already. What is f of x? What is L? What is our value C? It was 0 plus delta, which is right. We're just plugging in there now. Now we have to find, what we're looking for is a delta value. This, yeah. So basically, okay, we have to get rid of the absolute values, so we get when 0 is less than x, 0 in delta. Because what we're looking for is this. We have to try to get x by itself in here. How do we do that next? How do we get to x by itself?
You have to square both sides.
Yeah. Yeah, square everybody. Yeah, so this becomes epsilon squared. It's going to be absolute value of it. So, yes. When x is less than delta, so epsilon squared is equal to delta. For whatever values you're given. So if I said that epsilon equals 0.001, what would delta equal? 0.001 squared equals delta. Yes. Which is, yeah, I was laboring to try to produce yesterday.
Yeah, this epsilon delta.
Yeah, we make one step wrong and you lose everything. And there's so many rules. You have the trig rules, you have the algebra rules, and the manipulations. That's why it's a headache. Yeah, when we get to the shortcuts, life will be happy. Actually, we're coming up to, let me see how far, we're getting to an example here. We'll get to an example here. Now here, yeah, actually right now. Let's get to this one. Show that the sine of, this should be the sine of 1 over x, has no limit at x approaches 0 from either side as shown below. Why does it not have a limit? Exactly. I'm glad you said that. This is called an oscillating function. It oscillates between what two values? Yeah, the lowest it goes -1. And does it ever change from there? No, because the closer as x approaches 0, what happens to this curve? Well, at 1 point's -1, 1 point's +1, 1 point's -1. So we don't know. So does this one have a limit? No, because it goes to oscillating 2 different points. So as x approaches 0, the function well, no, we can't find it just yet. We will in a minute. Something similar to this, where we have oscillating functions. Oscillates between two distinct values. +1 and -1. Again, the closer it gets to 0, again, we don't know anything that's going on there because it just oscillates between up and down, up and down, up and down. The next thing we're going to talk about will be used a lot in this course. You will see it so many times. Because yeah, this is the first type. If you have an oscillating function and it's parametricized, it's got bounds, and you can't decide it. That's to come a lot of times when we talk about like exponential functions. We talk about exponential functions. What has to be true about the base? A has to be bigger than 1. If it's 1, it doesn't matter what the exponent is. It's always going to be 1. If it's 0, it doesn't matter what the exponent is. It's going to be 0. But if it's below 0, if it's negative, what happens to this function now? It oscillates. Does it? Because if we had -2 to the power x, when it's even, it's positive. When it's odd, it's negative. But unlike this one, we have 2 types of oscillating functions. We have what are called dampened, or not harmonic, but unbounded. When we talk about oscillating functions, as x goes to 0 or as x goes to infinity, one of 2 things can happen. Either they can be the same thing, they can dampen. It starts off big at both ends and then it gets down to narrow it to a certain point. That's called dampening. Or it can dampen as it starts off slow. I'm sorry. It starts off big, and then as x goes to infinity, it gets dampened. So that's the dampened example. Unbounded is just the opposite. It starts off tame, and then it gets bigger. Those are unbounded because it just keeps on going to infinity both directions, positive and negative. And they're oscillating. Those are all special cases, which we'll eventually talk about. So again, that's like you have to understand what the functions look like, what the graphs look like. Because if it's dampened or it's an unbounded oscillating function, you will never get an answer.
So a dampened one.
No, the dampened one, yes, because as well, the dampened one, if this is 0, as x approaches 0, you can't. So if it's going towards the dampening, it's going to be a solution. If it's going away from it, as x goes to infinity, it's now an unbounded frequency.
So okay, so a dampened one, it's really just a composition of like an
Unbounded that has restrictors on it.
Okay.
And actually, that's what engineers use a lot of times for airplanes, internal sounds. The cars, when they design cars, how do you dampen this road noise inside a car? Because if you've ever been in an old pickup truck and you drive on a highway or anything, you're deaf. You can't hear anything.
Yeah.
Except noise. But
Like cars from 2000, stuff like that.
that's true. And again, you sit in a car like a Lexus, where there's no road noise. I mean, you feel like you're in heaven. So, but yeah, because they have these artificial dampeners in the doors, in the chassis, and everywhere else that restrict the noise. Like that. And that's exactly what they use that for. All right, so now let's look at functions, limits involving functions like this. Sine theta over theta. Why is that important? As theta goes to 0, what is that going to approach? What do you think? Again, remember the first strike is always plug in the value. The sine of 0 over 0. What is sine of 0? What is 0? 0 over 0. Remember earlier we talked about if we had 0 over 0, we can do something. what we're gonna find out because of this, 0/0, in this example, it approaches 1. The function, the graph of this function is pretty interesting. It starts off pretty mellow. On both sides. But then when it's undefined at the origin, at 0. It's an open circle there. But because of the limit of the two-sided limits, they both approach which value? 1. So because of that, there's a whole proof of this using the sandwich theorem and using the trigonometric identities of a unit circle, and we look at internal angle versus an external angle, and yeah, it would have a 3-part thing that will draw out, and if you mess up one step, you mess the whole thing. So basically,
That's all the internal and then the external.
yeah, and it's again, it all goes down to this triangle versus this triangle, and then we have we're approximating that value, that secant line. So what's going to get to is we will have 3 parts of a function that eventually will end up with sine theta over theta equals 1 as theta goes to 0. But yeah, I don't want to get there because we have to talk about all sorts of the areas of hyperbolics and things like that. So I'm not going to talk about that. Yeah, I'm not going to talk about that. And that's what they call the squeeze or the sandwich theorem that we use. That's exactly what it's proving. Because if this one's 1 and this one's 1, the only way it could be true is if they are equal.
One can't be less.
Exactly. So it has to be 1. And so basically, we're looking at this. Actually, there's a theorem. Yeah, actually, there is a theorem. It says the limit of the ratio sine theta over theta as x or theta approaches 0. The limit as theta approaches 0 of sine theta over theta is 1. The beautiful thing about this is once the theorem has been stated, whenever you see any equation that's sine theta over theta, you know it's 1. You don't have to prove, you don't have to work anything out, just it's 1. So that's the cool thing about it. Again, it's proved by that. So this is a theorem that anytime you see sine theta over theta equals 1. Is it true for cosine theta? No, because at 0, it's 1/0, it's undefined.
So cosine, like cosine theta over theta as x approaches 1.
Then well, you wouldn't have one for theta for a cosine. What if you did have one for cosine? You'd have to convert it to a sine function.
Okay.
And that's where it gets complex. Because if you had cosine, then you'd have to convert it to 1 minus sine squared theta.
So there's
no. The proof is converting it from cosine to a sine function that will allow you to use theorem 7. Let's see if there's an example here. Yes, where's that? Oh. These guys. Involving sine x over x. This is what I just showed you. Well, yeah, there are. I mean, I think there's even one in the book, but the proof itself, as you see, it dampens out, goes in there. But the closer it gets to 0, the more active it becomes. And there's your theorem. Once the theorem's defined, then you're done.
It's great. You really just need to see the theorem. And it's not even, you don't even need to know the theorem.
Well, I can show you the proof if you want to see it. Let's go through it. Let me find it for you. I have it here somewhere. So so the proof of it is we're going to need one quadrant. And this is T. That's O. This is our point P. This is Q. And this is our point 1, 0. The unit circle, the radius is what? The radius is 1. So the vertical axis deals with the sine theta. And the horizontal axis deals with the cosine theta. So what would this long big one here represent? That represents the tangent theta. Why? Because it's tangential to the point there at 1, 0.
It's which,
Point 8, yeah. Because it goes on from there. So what we have to do first is the area of our triangle OAP. This is this big one here. Is less than the sector of OAP, which is less than the area of the triangle OAT. True. So OAP, the smaller one here, that triangle is less than this sector. What is the sector? This sector here. Of this sector. What does this sector represent? Because OAP includes this line right there. So it's this triangle. The sector includes the curve. So this inner triangle is less than that, which is less than the triangle OAT. True. Now let's put numbers to these guys. The area OAP is equal to half the base times the height. Which is equal to half. The base is 1, because that's the radius. And the height is sine theta, which is equal to 1/2 sine theta. So that's this part. That's the area of OAP. The area of the sector, of sector OAP is equal to 1/2 base times height, which is 1/2 . the radius times theta. Because remember, it's the arc. It's the arc length we're looking at. Which is r squared theta over 2. And the last one is the area of OAT. And that one's going to be 1/2 base times height, which is equal to 1/2. The base is 1 times the tangent of theta, which is equal to 1/2 tangent theta. So far, so good? So let's put these three together. Because remember, we have area of this inner, the area OAP, and then that one. So what we know is this. We have 1/2 sine theta is less than r squared theta over 2 is less than 1/2 tangent theta. What's the radius? So 1 squared is 1. So in the middle, we'll have theta over 2. Now, if we divide by 1/2 our sine over 2, if we divide each term by sine over 2, because we have to get rid of one of the bounds, because we have to start parameterizing these things. And that's going to get rid of this one. That's going to put sine theta over value in the middle. So sine over 2 over sine over 2 equals 1. Remember in the trig identities, we had cosine squared plus sine squared equals 1. What we did next is we divided each of them by cosine squared. We got 1 plus tangent squared equals cosecant squared. That's what we're doing here. We're just rewriting the terms. So what happens here? This becomes the 2's cancel, so we have theta over sine theta. So this is tangent over 2, flip that, so the 2's cancel, so we have tangent over sine. Well, yeah, that's what we're going to do next, because tangent is sine over cosine divided by sine, which now makes it, right, the sines cancel, so we have 1 over cosine. So far, so good? Reciprocate, flip everybody. Yes, but when you flip everybody, you also have to flip the signs. Yeah, so it's going to be because whenever you change you've changed it from where 1 is less than this, when you flip it, it's going to be now bigger than it. So that's it. So we actually have this right now. Oh, this one, we had sine cancels. So it should be cosine, I'm sorry. Well, you're right, good catch, yeah. This should be cosine, right? Yes. It really wouldn't have mattered because now as theta goes to 0, what happens? Even if it was 1 over cosine, cosine at 0 is what? It's 1. No, cosine at 0 is 1. Because at 0, cosine is 1. Sine is 0. So there you have the squeeze theorem. So sine of 0 over 0 is 1. Who'd ever thunk it? 0 over 0 equals 1.
Some of these proofs just require a tremendous amount of creativity.
Exactly. That's exactly what it is. You couldn't say it better. It is creativity. Is what function to use. The sheet I gave you, the chill cheat sheet in the very back, you can use any of those trig identities at any time to see what you get. Eventually, some of them you choose will be easier than others. You'll get the answer faster, but you'll get to the same answer either way. So that proves the theorem for us. So whenever we see sine theta over theta, as theta goes to 0, it equals 1. No more work needed for that. And because of our graph, it doesn't matter which direction you come through because both directions less than and greater than will be the left hand and right hand limits will give you the same value. Where's my shoot? There. Since you guys like trigonometry, here we have 2 examples. Show that the limit of cosine y minus 1 over y is 0, and the limit of sine 2x over 5x is 2 over 5. The limit as y approaches 0 of cosine y minus 1 over y. Prove that it's 0.
Not just cosine y minus 1 sine.
It's gonna be what? No, but it would be cosine squared minus 1 would be sine squared. Actually, we could use that. No, we couldn't use that. So we have to use another function. I don't have my sheet with me. Get your cheat sheets out and look at the back. Try the half angles. Because we want to keep away from here. What's this? Using sine x over 2 equals radical 1 minus cosine x over 2. Now, the reason this is positive or negative, because notice ours is cosine minus 1. Which first off, we'd have to square both sides. So we have sine squared y over 2 equals 1 minus cosine x over 2. Multiply both sides by 2.
Why do we use, y over two?
Because that's where we're using r as our angle. Minus cosine y. Subtract 1. So it's 2 sine squared y over 2 minus 1 equals negative cosine y. And change the sign. So far, so good? Yeah, so there's the creativity we were talking about earlier. Since we use this formula, square both sides, we'll isolate cosine. Actually, no, we have cosine minus 1. And no, I have to keep this not. I went too far. So we have cosine y minus 1. And here we have 1 minus cosine y. How do we fix that? We have to get cosine y minus 1. And in the equation, we have 1 minus cosine y.
When we change it to sine,
No, just take the negative of it. Because then we have cosine y minus 1.
We'll get two sides. Cosine y.
Right. So our now we have minus 2 sine squared y over 2 divided by y, of course. The denominator is still the same. Y goes to 0. Okay, yeah. Well, our objective here is what we just talked about was the limit of sine theta over theta as theta goes to 0 equals 1, right? Look what we have here. We have negative 2. So this 2 would be the same as if it was below that. So we have limit as y approaches 0 of negative sine squared y over 2 y over 2. These are still the same values because now I can say change theta anywhere you see y over 2. So now we get the negative goes out in front, the limit as theta goes to 0, since we changed it to thetas. Sine theta over theta. If I do this square,
Square root.
no, it becomes times sine theta. I'll just split them up. Because I need to have this for sure. What does sine theta over theta become? 1. But as we have sine theta as theta goes to 0, sine of 0 goes to 0. All that for nothing. Yeah, it was all because this is squared here that ruined it for us.
All that.
But 0 is our value. That's our limit. So the hardest part of this one is finding a conversion that would work. Because we know what we had. We had cosine y minus 1. We had to find something with 1 minus cosine minus 1. And then from there, algebraically manipulate it. Let's do number B. B, the limit as x approaches 0 of sine 2x over 5x, prove that it equals 2 over 5. There is there's something we can do in trigonometry that pretty much, if we just take out, just remove that, because it's 2 times sine theta is 2, same as 2 sine theta.
Well, isn't the double angle identity for two, or for sine 2x, wouldn't that be 2 sine theta times cosine theta?
Yes, 2 sine theta cosine theta. This is a constant, so it can go out in front. So we have sine x over x times cosine x. This, as x goes to 0, becomes 1. Cosine of 0 becomes 1. So we have 2 over 5 times 1, which is 2 over 5, which is what we're trying to prove. Yay! Now's the time to celebrate. Yeah, yeah, here for the home team. Again, is the calculus hard? No, it's the algebra and trigonometry. That's the hard part. We have to make it fit in there. Okay, so okay.
You go back to the other two.
Let's look at example 6. Where's my example sheet? Well, the double angle of sine 2x equals 2 sine x cosine x. Yeah, if you ever get away from squared or multiple angles, then it makes it much easier for us. Got it? All right, let's look at example 6. Find the limit of tangent t secant double angle t over 3t as t goes to 0. Okay, let's first get rid of this one. Put this out in here. And then we have tangent is what? Sine over cosine. And secant is, well, secant double angle. 1 over cosine 2t, isn't it? Secant squared. Or secant double angle. I believe that's cosine 2t. Well, let's see them. What is secant? Secant is 1 over cosine 2t. Well, yeah, so we'll do that. We'll do 1 over cosine 2t, because then we can find the cosine double angle in here. Either the 1 minus 2 sine squared or 2 cosine squared minus 1. Yeah, cosine's got a lot of them. So we don't have a shortage of we can try. All right.
That's fine, right?
What's that? Yeah, that's what we change this to this. That's tangent, right? So let's see where we can go from here. So the 1/3 can come out, it's a constant. As t goes to 0, we can rewrite sine t over t. That combines these two. We have 1 over cosine t, 1 over cosine 2t. So far, so good. Because yeah, this is what I'm looking, trying to get this first. Once I have that, this is going to be gone. That becomes 1 as t goes to 0. So now all we have to do is figure out what to do with these. But since they're cosines at 0, what happens at cosine of 0? It becomes 1. So it's 1 over 1, 1 over 1. So it's 1/3 times 1 times 1 equals 1/3. For the next one. Yes, at 0, whenever we go to 0. But we want 0 because we're looking for sine t over t. So we want it to go to 0. Whereas if it was going somewhere else, if it was going to infinity, we couldn't use that. We have to find something else. Where are my questions? Win number 2. Oh, you're looking at something. What are you looking at?
Oh, what?
You're deep in thought.
Oh, no, I was just, reading over that last one.
Okay. Oh,
It's fine, yeah.
this is straightforward.
Yeah,
once we got everything co-tangent. So our last one. Show that for non-zero constants A and B, the limit as theta goes to zero of sine A theta over sine B theta equals A over B.
It's in A sine. Beta equals B.
Okay, let's look at that. That sounds good. So this is A sine theta cosine theta, B sine theta cosine theta.
Because of the
But okay, in reality, that would only work if A and B were twos, because that only works on a double angle. But it looks good. But no, let's look at another way if we can do this.
but could you do if it were like a any even number, could you do some type of a variation? If it were like a quadruple.
But then we have to come up with one thing that's universal throughout them. We could if it was only even integers, but it could be odd integers as well. So now we have a problem.
Okay.
But yeah, that was a good try. I'll give you points for that one. I like it, but we have to look for something more. We have sine A theta over sine B theta. If we split them up, what can we do with them? Because remember, we need to have on the bottom here to make it disappear. On the bottom, we have to have A theta. So in order to put that there, we'd have to multiply across the board by A theta or B theta over A theta. Okay, let's look at if we multiply everybody by A theta. Because this is just one. Because we have to have the A and the B we have to take care of. I'm gonna put X instead of theta. So now I have the limit of sine AX times 1 over sine BX. So that means this A can go under here. That B can go out here. This A can go out here, and this B can go there. So I have the limit as X approaches 0. Can't see it. Of sine AX over AX. That takes care of that one. Times BX over sine BX. That takes care of that one. Times AX over BX. and the x cancels. So we have a and b. As x goes to 0, that goes to where? 1. So we have the limit, well, a and b, because that's a constant. It has to be the same thing. It has to go to 1 also. Because remember in our example where we flipped it, what if we didn't flip it, kept it upside down? It would still be 1 to 1. So this goes to 1 also. All we have left is, because the x is canceled, all I have is a and b. So the theorem 7 says the limit as x approaches 0 of sine x over x equals 1, which is the same thing as the limit as x approaches 0 of x over sine x. Because in our derivation, the last step we flipped them. If we didn't flip it, we still get the same thing.
Right.
So this is a corollary of theorem 7, is sine x over x or x over sine x, as x goes to 0, will go to the same place.
Because it's still 0.
It's 0 over 0. Right.
It essentially is.
So there you go. That's everything for that section.